the idea of dispersive waves, it's motivated by our formal series solution of the wave equation, in which we see that we have a wave in the x variable being multiplied to a wave in the t variable. So we generalize this idea. We say, okay, well, let's assume our solution u of xt now has this general form of being a wave in the x variable and a wave in the t variable. And so here, we should think of these in terms of Euler's formula, where that's a cosine kx plus I sine kx, for example. And, and the minus sign there is just there for notational convenience. So here, whoops, that's not what I want to do. So here, this minus sign is just there for notational convenience. In a more general setting, we might assume u of xt has this form without the minus sign. So my research area involves, in PDEs, involves what's known as asymptotic scales or multi-scales analysis. So it's a way of solving the PDE by using kind of sort of a Taylor series type approach. So the dispersive waves, they're kind of new to me. So there's some things that with dispersive waves, I'm still trying to, understand myself. So how does the solution technique work? It's fairly straightforward. We will assume the solution has this dispersive waveform and then plug it in to U. So in the PDE now, I'm going to replace U by e to the I, kx minus omega t in the actual PDE. And then you'll get an equation. So I'll show you an example here. So just to actually try to interpret a little bit, what does all this notation mean? What exactly is the k? What exactly is the omega? How can we interpret this as a wave? So just to study the anatomy of the wave here, the first thing to keep in mind that for ikx, this is a wave that's happening, with respect to the x variable, our spatial variable. And if you think of e to the I kx as cosine kx plus I sine kx, then the period of the wave is 2 pi over k. So here, k represents the number of waves per 2 pi distance. And similarly, for the other part of the solution, again, we have a wave that's in the t variable here. And again, if you think of e to the minus I omega t as cosine omega t minus I sine omega t, then this wave has period 2 pi over omega. So here, k and omega are related to the frequency of the wave. In one case, it's related to the frequency, the physical frequency. How many waves do you actually see? And the other case, it's related to the temporal frequency. In a certain amount of time, how many waves are going to go by? And so if we actually divide one term by the other and kind of look at the units, so now if I do the temporal frequency divided by the spatial frequency and kind of analyze the units, we get that this is actually some type of velocity. It's distance over time. It's some type of velocity. If you think now perhaps of an ocean wave, or I guess any kind of wave, as it physically moves, there's something driving the motion. And here it's perhaps this combination of space and time. And so now when we look at this function, we can think of it as a wave where we can say, aha, k represents the wave number. That's the frequency, right? So if you're thinking, of just a simple sine curve. We're talking about how frequent the curve is. And you think about in the ocean where you have multiple waves of different frequencies and they're all interacting. Okay. So K is the frequency, and here omega over K, we can interpret as some type of velocity, some type of phase velocity, wave velocity, that's somehow driving the motion or capturing the motion of the wave. And so now we can define what's known as a linear dispersive wave. So a linear dispersive wave is a wave form of this type where omega is a function of K. So here we could conceivably replace omega now with some, function involving K. Maybe omega equals K squared or omega equals 2K. I don't know, I'm just making up stuff. But if omega is now a function of K, then we've got what's called a linear dispersive wave. And we can talk about if the phase velocity is not constant with respect to K, then we can say we have a dispersive problem, a wave propagation problem that is classified as being a dispersive wave propagation problem. So we have the idea of a dispersive wave and the idea of a wave propagation problem that's classified as being, of a dispersive type, dispersive nature. So at this point, you want to, I think, to think about waves in the ocean and how we have waves of different wavelengths, different velocities, and how they interact in the ocean, So that's kind of what we're kind of headed towards. Here, the omega term, when we're dealing with a linear dispersive wave, kind of relates time and space. And here, if you look at the omega term here, I write it this way, where I have omega as a coefficient in the front, and you have t over k. So t has to do with time and k has to do with the spatial variable. And you think about how this relationship changes if omega is equal to 2, or if omega is equal to 1, or if omega is equal to 1/2. It's regulating this ratio between time and space up there. And so now let's actually use a dispersive wave to solve a PDE. And when we solve the PDE, you'll see that omega of K, when we plug in the dispersive wave into the PDE and solve for omega, omega ends up capturing all the information about the PDE. That's how, the PDE will inform what the solution of omega looks like. It'll depend on the PDE. The boundary conditions and initial conditions are something we will then deal with later. So here, I just want to show you the technique, first of all, of how do we use a dispersive wave to, formulate a solution, to create a formal solution. I'm not solving the traditional wave equation here. This is a wave equation with a so-called stiffness term. And we have, our conditions, our initial conditions here. So now what I want to do is to solve this, to find the so-called dispersion relation and to solve the PDE. And when we say use dispersive waves, what does that mean? It means we're making this assumption that u of xt has this form. And so what are we going to do with this now? We're going to put this function into the PDE here. For u now, we're going to replace u with e to the I kx minus I omega t. And so that's what I'm doing down here. Here I'm calculating the partials. So now I've got this function, and I want to calculate 2 time derivatives. So here, when I'm taking the derivative with respect to t, anything that's not a t variable is treated like a constant and differentiates to 0. So here, what we get is the minus I omega comes down one time when you differentiate. This minus I omega will come down when you take a first derivative. Take a second derivative, you get another copy of minus I omega. The minus signs cancel. I omega gets squared. And that's where this term is coming from. And then you copy down the exponential term. And then I omega squared is just I omega times I omega. So this is I squared omega squared, but I squared, that's supposed to be an omega, but I squared is -1. And here, e to the I kx omega t, well, that's just what we're calling u. So that's where this u is coming from right here. And here, this term, I omega squared, is right here. And similarly, I calculate this second spatial derivative with respect to x here. So now we're looking at this function, take the derivative with respect to x. So you look at the exponent, anything that's not an x will differentiate to 0. So it's just the ikx that survives, and we differentiate it twice. We get 2 copies of ikx. So I get an ik squared when you take the derivative with respect to x. The c squared is being multiplied from the PDE. There's the exponential term that we copy down after taking the derivative. But this dispersive wave is exactly what we're assuming is u. And here, ik squared, is I squared times k squared, and I squared is a -1. And so that's where this -1 is coming from here. And I'll let you check here, this final term, the stiffness term, will look like this. So what we're doing now is, I'm going to set this function, which is the left-hand side of my equation, equal to the right-hand side. So this function here, oops, no, let me do this one here. This function, which is our spatial term here from the wave equation, minus that stiffness term. So here's the stiffness term. And I want to subtract this stiffness term. So you do that, we get this nice harmless looking equation right here. So now, we're basically now doing algebra. How do you like that? Doing algebra to solve a PDE. So what are we solving for? Omega. Here, the assumption is that since we're dealing with a linear dispersive wave, omega is a function of k. So I'm solving, we had omega and k, and now I'm saying omega is a function of k. So I just want to solve for omega. And then I can plug in to this expression. K is just k. K is any real number. Omega here will be some function that I'm looking for. Once I know what omega is, and I can plug it right there, then we'll have a form for the linear dispersive wave. So now we're doing algebra. Okay, so I want to solve, so I'm going to multiply both sides by the minus sign and divide and cancel the u's. So here, the term u, which is the exponential term, and it's, not 0. It's u is just the exponential. So cancel the u's and minus multiplied through by a minus sign. So that becomes positive, that becomes positive, that becomes positive. So I have omega squared equals c squared k squared plus alpha squared k to the 4th. And now take the square root of both sides. I get omega of k is plus or minus And here I factored out. So I did a little algebra, I skipped a step. Here, when you take the square root, there's a common term of a k squared, which I factored out. You factor out the k squared under the root, square root of k squared becomes k. So that's where this k is coming from. And that's why this is a k squared instead of a fourth. I factored out the k under the root. So now we have two. So if you look here, we have two solutions for omega, a plus minus from taking the square root. So that's no problem. I'm now going to plug it into our dispersive wave, and we'll get, basically our basis of solutions is two dispersive waves. And here I factored out, so the omega has a k in it. So here, there's this k right here. Maybe I'll use a brighter color. There's this k right here. And then there's a k right in the front of the omega answer. So these two k's I've factored out here. This one and this one. That's what's appearing right here. I factored it out. And the I as well, because they both have an I. And then you have the kx minus I. Omega is plus minus k square root c squared equals alpha, blah, blah. So here are my two waves. And now, this isn't our first PDE rodeo. We've been around. We're hip. We know what's up. We've got two solutions. What are we going to do? We'll use superposition to combine them. Okay? Because here the PDE is linear, can be shown to be linear. And since k is over all reals, this isn't going to be a Fourier series. This is going to be a Fourier integral, what we call the inverse transform. So here, the summing will be in the form of an integral. When I say summing, that's in the form of an integral. And then our coefficients, here this is a of k and b of k. So here I don't write a sub k, because now k is a real number. K is not, before when you think about your Fourier series, we wrote a sub n or a sub k. That was when n was an integer. Here, this was when n was equal to, 0, 1, 2, so on and so forth. Now, and our Fourier coefficients formed a sequence before. Now, this is our Fourier coefficient, but k is a real number. So I don't want to use our traditional sequence notation. I don't want to write it this way, because we typically use that notation for sequences when k is an integer. When k is all real numbers, like when you have a function of all reals, right? What do we do in calculus? We say y equals f of x, when you have a function of real numbers. And that's really the different notation. A sub k, that's also function notation, right? It's just this is a function where the domain are the integers. And here y equals f of x, that's function notation where the domain are the reals. So here, instead of writing a sub k, I'm writing a of k, because that's your coefficient, but it's a function of all reals. That's also, part of eventually what becomes part of the transform. Remember, the Fourier transform is really just a Fourier coefficient. So yeah, so we've got our two coefficients. Instead of a sub k, I'm writing a of k, because so here's a, that would be sub k if this is a series, but a of k. And b sub k if that was a series, but it's not. It's b of k, because k is, ranging from minus infinity to infinity. So there's our general form of the solution, that satisfies the PDE only. And here, when we solved for omega, remember this comes from solving this equation here, which completely 100% comes from the PDE. The equation comes from the PDE, and from the equation we find omega. That's why we say omega has all of the PDE information encoded in it, because omega is directly found from using the linear dispersive wave assumption and the PDE. That's all. So now we have to find the coefficients. And so we still haven't used these initial conditions. So if you plug in a 0 for t now, so I'm going to plug in a 0 for t, you're going to get something that doesn't have a t variable in it anymore. And if you look at this, if we take a look at what we have, this is actually a Fourier series. This is a sum. Here are the coefficients times the basis element. This is actually a Fourier series, what we call the inverse transform. And here, and so I use that notation. So this is actually turned out to be the inverse transform, what we've called the inverse transform of whatever coefficient is right here. If you want to think of this as a single coefficient for right now, you can just think of that as some C of k. This coefficient is what we call the Fourier transform, and this would be the inverse transform. So now if I hit both sides with the Fourier transform, Fourier both sides, I get a formula for A of k plus B of k is the Fourier transform of U of x. So what I did was, that's supposed to be a Fourier. Apply a Fourier to both sides. Here it cancels out, Fourier transform inverse, and here you have the transform of U of x. And now we have a formula for this. We have a formula for, we have a formula for how to find the Fourier transform of U of x. The formula is, it's just a projection formula. The Fourier transform is actually just a Fourier coefficient. And here what we're doing is just a projection. That's an inner product, U of x, inner product with e to the ikx, which is the basis element. And it's like a L2, L inner product, so you're integrating. And here that's just the normalizing. You know, it's like F inner product V divided by norm V squared, right? The generic vector projection formula. So that's all we're doing, just doing vector projection. And we can now take the derivative of both sides with respect to t of this thing. Take the t derivative of both sides, bring the derivative inside the integral, and then let t equal 0. You'll get another equation that's equal to v. And it'll be, again, you know, a Fourier integral, an inverse transform. And you'll be able to do exactly what we've done above here to figure out, you know, an equation for A of k plus B of k. And so if you take the derivative and do exactly the same procedure we did above, you might want to practice it, you know, for fun. There weren't any dispersive wave problems on the homework, but it's exactly the same procedure. Only difference is we first take a derivative. So here I'm going to do derivative with respect to t on both sides, bring the derivative inside, and then let t equal 0 and set the whole thing equal to v of x. And then work the transforms, just like what we did here. Whoops. Just like up here, once we get it equal to the function, we work the transforms. So now I have two equations, two unknowns. And so we can solve for A and B. So two equations, two unknowns. So I solve for A of k and B of k. And that's what are the missing coefficients from our solution. That's the only part that's missing. Remember, if this was a series, we would write this as A sub k. And so don't let the notation mess with you, but appreciate what's happening. In the series case, our coefficients were indexed by integers, so we use sequence notation. In the transform case, our coefficients are indexed by real numbers, so we use function notation. And here, k, ranges from -infinity to infinity. So that was an example of how we use dispersive waves to solve a PDE. So I kind of now want to move towards analyzing kind of ocean waves. So this is now slightly changing gears a little bit to talk more about, closer to Harvey's research interests, the ocean waves stuff. So we're starting out with the simple idea of wanting to analyze the physical interaction of waves that are physically close. Physical interaction of waves that are physically close. I guess like the ocean. I don't know. What's happening at the ocean? When you're at the ocean, what's the correct way to think of the wave? So here's the beach. I'm standing on the beach looking at the waves. Am I looking at waves that are going up and down? Is that how I'm thinking of the ocean? Or let me do the overhead bird's eye view. So this is, if we look from above, is it waves that are going back and forth like this? Is that what I'm seeing if we look from above? What's going on with the old ocean waves, folks? So you remember, we talked about a string that went back and forth. So is the string kind of horizontal, pushing back and forth, and is that what's creating waves? Or is this string vertical here, going up and down, or is it both? Oh, nice one, nature. Is it both? So things to now start to think about, okay, how do waves actually move? And if you're at the beach, you see the waves lap up at different frequencies. How come all the waves don't get there at once? Why do they, So what's going on here? So, okay. So let's start by analyzing waves that are physically close. For, baby steps, let's just look at the case where we have two simple waves of the form cosine kx minus omega t, where omega is a function of k. And here we'll have two wave numbers k and k plus delta x. So think about what that means. K has to do with the frequency on the x-axis. Okay, so I've got a wave here with some frequency, and then I want another wave with basically very close but slightly smaller frequency. And here are my two waves. One has wave number k, one has wave number k plus delta x. One wave will be slightly longer in wavelength or shorter in wavelength than the other, right? One will have period 2 pi over k, and that'll be one wavelength, and the other will have a slightly longer or shorter wavelength, I should say, because if I divide by a bigger number, it's a smaller fraction, and k plus delta x, delta k will be slightly bigger. So this will be a shorter wavelength, and this will be a slightly longer wavelength. And we want to know, how are they going to interact with each other? So here's my two waves, wave number k plus delta x, right? You have a wave and then a slightly shorter wavelength wave, k plus delta x in there. And so now let's begin the mathematical analysis. So this is kind of, we draw the border here. That's where the physical stuff stops. And now we're going to let the math take over. And here we want to kind of analyze what's the math telling us about the physical situation. Now we want to try and reconcile our intuition with the math. So here we use an identity, and we can rewrite this sum. So here you should know there's this sum here. Now we've rewritten it as a product, where in the identity requires us to combine the arguments of these different cosine functions, and which is what I've done here, and I've simplified, where, you know, this would be A and this would be B. And so I rewrite it as this product. Okay, so now let's analyze it. So now here's what our two waves interacting, our two waves that are close together interacting. We've rewritten their formula in this way as a product. And if we look at the wavelength for this in X, the wavelength in X, I want to take 2 pi and divide it by k plus delta k over 2. Again, on the other side here, for this other wave, we want to look at the wavelength in X. So I take 2 pi and divide it by delta k over 2. And so here, if you compare them, we have, I'm calling this the long wave, and I'm calling this the short wave, because here the denominator is bigger. Here you can rewrite this and multiply top and bottom by 2. So you can rewrite this as 4 pi over 2k plus delta k. And you can see this has a bigger denominator. So this has a shorter, this is a smaller fraction. So we have our so-called short wave. Sorry, I want to be in this box thingy. We have our short wave versus long wave here. And so now we want to try and understand, okay, what's going on here? What's up with the short wave? What's up with the long wave? And how are they interacting with each other? Okay, so here it might be best to show you the picture first. And so the theory is, when we graph these things, you know, it turns out that the long wave acts as what we call a wave envelope of the short wave. So let me go to the picture. And so here, if you graph it, the graph is this dark curve. That's the graph. But if you graph the long wave, so here the dashed line is the graph of just the long wave part. It turns out the long wave seems to encompass or envelop or surround the wave, at least mathematically, if you look at the graph. And we kind of think of as the long wave as being a shepherd that shepherds along the actual wave. And here we can analyze the velocity of the waves here. So this is kind of distance over time type of calculation. It's not exactly time. It's how much space has been covered over this period of delta k as the wave number changes. It's kind of a velocity with reference to the changing wave number. And so here we're taking the time components here, the time components, and trying to calculate, you know, how that's changing as the delta k is changing. And we can motivate this idea of a group velocity with this type of calculation. You can see it looks just like a change in position or change in, you know, here this term is referring to the t. Think about what happens to the wave as time moves. You know, we had the space wave and the time wave. So it's this change in whatever's happening with the time wave as a function of this change in the frequency of the space wave. And we can also motivate a velocity for the short wave using its time component. So here again, we're using this time component to kind of calculate how is that part changing as the frequency number changes. And so we can motivate this two different velocities. And the idea is that the bigger group velocity, that's the velocity of this outer wave, that's the wave envelope, has the group velocity. And then you have the actual wave in here, that's moving at the so-called phase velocity, you know. So the whole idea is to, when we look at this mathematical expression, try and interpret, what does this part of the wave, what does this part of the solution, you know, mean, and what does this part of the solution mean? And if you graph this portion, you can get that bigger wave. That's the dashed line. And, you know, we can try and analyze using the information we have about the frequency, both the space frequency and time frequency, to make a phase velocity, analysis, just like we did up here, where we use the temporal and spatial frequencies to do a phase velocity analysis. That's essentially all we're doing. The omega over k is that phase velocity analysis from the discussion back there. So yeah, so in terms of these waves in the ocean, perhaps, you know, we start to see that, and, you know, in the ocean, of course, there's more than two waves interacting, right? So we start to suspect this is the type of structure from the interactions of the waves. You get this, group velocity and phase velocity, and that kind of drives the waves, you know. So here, in particular now, I want to start talking about what's called deep water waves and move closer towards analyzing what happens at the ocean. Okay. And as I said, you know, the group velocity is kind of considered to sort of be a type of a shepherd that's kind of moving the thing, you know. The phase velocity is more, I don't know, more local. Group velocity is more macro, you know, macro, micro. So here, let's look at a deep water wave. Okay, so here we're gonna, for deep water waves, it can be shown the dispersive, you know, wave equation, the dispersion relation for these water waves has this form. So I don't derive this from the PDE. I do think it's in the book, I can't remember, but it's something that involves gravity. So gravity right here, and then some other terms like surface tension. So perhaps that's where the hyperbolic tangent's coming from. And here, the height of the water also, you know, is making an appearance. So be careful. This h is a variable. That's just the hyperbolic tangent. So h there is the height of the water. G is our gravity. K is our wave number. And the tangent and all that, that's from taking into account surface tension. You know, I don't look at the original PDE that they solved. So they have some PDE modeling these deep water waves. So, you know, if you think about for very deep water waves, so if H is the depth of the water and we have very deep water, like out in the deep ocean, then here I'm going to take a limit, send H to infinity. If you remember your Calc 1 hyperbolic tangent graph, which I didn't, so that's why I put the graph up here, as H goes to infinity, KH goes to infinity, this term approaches 1. This hyperbolic term approaches 1. So for very deep water waves, we can actually drop this part. For when H is very large, we can actually replace the hyperbolic tangent part with just a 1. So let me calculate the phase velocity here. Let me calculate the phase velocity of the short wave in deep water. Okay, so the couple of things, phase velocity of the short wave, and we're in deep water here. So H is large. And so we have our omega k over k from before, from the limiting process. Here, the dispersion relation is this function. And I cancel, what happened there? Oh, I cancel the k's. So this k and this k, see, the square root now comes down to the denominator. Okay, so I have a square root of k upstairs and a k downstairs. You cancel, you get a square root of k downstairs. So then I put everything over a single root. Now I send h to infinity and replace the hyperbolic. So now let the depth of the water become very deep. So that term goes to 1. And so for our phase velocity for short waves in deep water is root of g over k. And here we know that the period, the length of a wave is 2 pi over k. 2 pi over k is the period of the wave. And so, that's the length here. So that's L. And so I can solve for k. So here, k equals 2 pi over L. And so now I have a formula for the phase velocity that involves gravity and the length of the wave. Or you even look at this formula, involves gravity and the wave number. So one thing the math is telling us, which I think is interesting, is that in the deep water situation, here we have a dispersive scenario, because here the phase velocity is a function of k. The phase velocity is not constant. And so here we have a dispersive problem here. Short waves in deep water are dispersive. So you have motion, they're moving. Short waves in deep water, they have some kind of phase velocity that's dependent on the frequency of the wave. The choppier it is, the bigger the, something that'll affect the phase velocity. If it's not as, so you're this behavior in the ocean, we can sort of start to mathematically explain, like, why does the ocean behave this way? For the group velocity of the wave envelope, again, I'm gonna, for large h, I let that hyperbolic tangent term be equal to 1. And if we use, from before, we derived this formula for the group velocity as the derivative of the dispersion relation. So here I take the k derivative of the root of g of k, and we get a formula here. So here's the formula. And then we use the relationship between k and L. So I rewrite it. We have here, it's the same formula in 2 different versions here. And so for the group velocity, we can see that it's half the phase velocity in deep water. And the longer waves, the waves with lower k numbers, remember, the smaller the denominator, the bigger the fraction. So the longer waves, the ones with the lower wave numbers, will have large group velocities. All right, let me get this part. Well, distance wireless sooner is like 1/2 the phase velocity. I don't know. I'm sure this makes sense because it's math, but I'm not getting it right now. But yeah, so I'll let you read this. Here's some wonderful things. The role of gravity, I think, is pretty interesting in the waves. You can see here for this shallow water analysis. So you have to be careful. We did deep water versus shallow water. And then we did the analysis in deep water for the group velocity and phase velocity. And for shallow water, here we're looking at the analysis of the phase velocity. And in shallow water, we still make the hyperbolic tangent term disappear. So here, I just rewrote this. I multiplied in the bottom by an h and the top by an h. And for shallow water, I'm sending H to 0. And so if you send H to 0, you get 0 over 0. And so you can use L'Hopital's rule to show this term here as H goes to 0, just goes to 1. So in the shallow water case, you can see that gravity plays a factor and the depth of the water plays a factor in the phase velocity. And this is different in the deep water case. In the deep water case, for the phase velocity, you'll see that the depth of the water does not seem to factor in at all for the phase velocity. You know, the wavelengths is important, gravity is important, the depth of the water does not seem to be important. I mean, I guess physically that's reasonable, right? It seems to match our intuition. All right, folks, my brain's fried.